The universe, a vast and mysterious realm filled with wonders that have captivated humanity for millennia. Yet, behind its beauty lies a hidden threat, a silent menace that could cripple our technological civilization. Cosmic radiation, solar flares, and electromagnetic interference pose significant challenges to the computers we rely on, both in space and on Earth. Understanding these threats and developing innovative solutions is crucial as we venture further into the cosmos. Our future in space, and indeed the future of our technological civilization, depends on our ability to protect our computers from the hostile environment of space. Cosmic rays, the silent travelers of the cosmos, pose a constant threat to our technological infrastructure. These high-energy particles, originating from distant supernova and active galactic nuclei, zip through space at nearly the speed of light. When they collide with atoms in the Earth's atmosphere, they create a shower of secondary particles that can penetrate even our planet's protective layers. These particles, like microscopic bullets, can wreak havoc on sensitive electronic components. The impact of a single cosmic ray can be enough to flip a bit in a computer's memory, potentially leading to software crashes or data corruption. In more severe cases, cosmic rays can cause physical damage to transistors and other components, shortening the lifespan of electronic devices. For satellites and spacecraft, this threat is even more pronounced. Protecting these critical assets from cosmic rays is paramount for ensuring the reliability and longevity of space missions. The effects of cosmic radiation are not limited to space-based systems. They can also impact ground-based infrastructure. Developing innovative shielding techniques and radiation-hardened electronics is essential for ensuring the reliability of our technology in the face of this ever-present cosmic threat. The Sun, the life-giver of our solar system, can also be a source of immense disruption. While it bathes our planet in light and warmth, it also unleashes powerful bursts of energy known as solar flares and coronal mass ejections, CMEs. These events can have significant impacts on Earth's technological infrastructure. Solar flares release massive amounts of energy, including X-rays and ultraviolet radiation, which can interfere with radio communications and disrupt satellite operations. CMEs, on the other hand, are large expulsions of plasma and magnetic fields from the Sun's corona. When a CME reaches Earth, it can interact with our planet's magnetic field, triggering geomagnetic storms. These storms can induce powerful currents in power grids, leading to widespread blackouts and damage to transformers. Protecting our technological infrastructure from the wrath of the Sun requires a multi-pronged approach. Space weather forecasting plays a crucial role in providing early warnings of solar storms, allowing satellite operators and power grid managers to take mitigating actions. Investing in space weather research, developing advanced forecasting capabilities, and hardening critical infrastructure are essential steps in safeguarding our technological future from the Sun's fury. Protecting our technological assets in the harsh environment of space requires innovative solutions. Shielding is one of the primary strategies employed to protect sensitive electronic components from space radiation. Engineers have turned to lightweight materials with high atomic numbers, such as aluminum, titanium, and tantalum, to create effective radiation shields for spacecraft and satellites. These materials are more effective at absorbing and scattering radiation than lighter elements, providing a greater level of protection for sensitive electronics. In addition to passive shielding, active shielding techniques are being explored to provide dynamic and adaptable protection against space radiation. One such approach involves using superconducting magnets to create a miniature magnetosphere around the spacecraft. Another active shielding concept involves using electrostatic fields to deflect charged particles away from sensitive electronics. Electrostatic shielding systems typically involve a grid of charged wires or plates that create an electric field, repelling charged particles and diverting them away from the protected area. Section 5. The future of spacefaring, computing, innovation and resilience. As we venture further into the cosmos, the need for resilient, radiation-hardened computing will become paramount. Traditional approaches to shielding will become increasingly challenging as mission durations increase and spacecraft venture further from Earth's protective magnetosphere. The future of spacefaring computing lies in a combination of innovative shielding techniques, radiation-tolerant materials, and fault-tolerant designs. One promising area of research is the development of radiation-hardened electronics, specifically designed to withstand the damaging effects of space radiation. Another avenue of innovation lies in the development of software-based fault tolerance techniques. Redundancy, where multiple copies of critical data and software are maintained, is a common approach to fault tolerance. Moreover, researchers are exploring the use of artificial intelligence and machine learning to develop more sophisticated fault detection and recovery systems. By combining radiation-hardened electronics, software-based fault tolerance and intelligent systems, we can create a new generation of spacefaring computers capable of withstanding the rigors of deep space exploration. Section 6. Beyond shielding, rethinking computer design. While shielding plays a crucial role in protecting space-based electronics, it is not a complete solution. Traditional computer architectures, optimized for performance and cost on Earth, may not be suitable for the harsh realities of space. One approach is to move away from the traditional centralized computing model towards a more distributed architecture. In a distributed system, multiple interconnected processors share the workload, reducing the impact of a single component failure. Another promising area of research is neuromorphic computing, which draws inspiration from the structure and function of the human brain. Neuromorphic chips, designed to mimic the interconnected neurons and synapses of the brain, offer inherent fault tolerance. Exploring alternative computing paradigms such as quantum computing and optical computing could lead to the development of inherently radiation-resistant computing systems. While hardware innovations are essential for creating radiation-resistant computers, software plays an equally crucial role. Software can be designed to detect and recover from errors caused by radiation, mitigate the effects of component degradation, and provide a layer of redundancy to critical functions. Error detection and correction codes are essential for protecting data integrity in the harsh environment of space. These codes introduce redundancy into data, allowing errors introduced by radiation to be detected and corrected. Software can also play a role in mitigating the effects of component degradation caused by radiation exposure. As electronic components age in space, their performance gradually degrades. Software can be designed to compensate for this degradation, adjusting operating parameters and dynamically allocating resources to maintain system stability and performance. Software virtualization techniques can create virtual instances of hardware components, providing a level of redundancy and fault tolerance. The challenges posed by the hostile environment of space are not confined to any single nation. They are a global concern. International collaboration is essential for sharing knowledge, pooling resources, and developing innovative solutions to protect our technological infrastructure. Space agencies worldwide, such as NASA, ESA, JAXA, and others, are actively engaged in research and development efforts focused on mitigating the effects of space radiation and solar activity. Collaborative projects, such as the International Space Station, provide valuable platforms for conducting experiments, testing new technologies, and gathering data on the space environment. Sharing data and findings from these missions is crucial for advancing our understanding of space weather and developing effective mitigation strategies. International standards and best practices for radiation hardening and space weather resilience can help ensure the interoperability of systems developed by different countries and organizations. By adopting common standards, we can facilitate collaboration, reduce costs, and accelerate the development of innovative solutions. Open communication and data sharing among researchers, engineers and policymakers worldwide are essential for fostering a global community dedicated to addressing the challenges of the hostile universe. The increasing demand for computing power in space, driven by scientific exploration, commercial applications, and human spaceflight, presents both challenges and opportunities. Traditional ground-based data centers, while offering vast computing resources, are limited by the speed of light. The latency inherent in communicating with Earth from distant locations such as Mars makes real-time control and data analysis impractical. Space-based computing, where data processing and analysis occur closer to the source, offers a solution to the latency problem and enables new possibilities for space exploration and utilization. For example, space-based data centers could process the vast amounts of data generated by telescopes and scientific instruments, transmitting only the most valuable information back to Earth. This would significantly reduce the amount of data that needs to be transmitted over long distances, saving time and bandwidth. However, deploying and operating computing infrastructure in space presents significant challenges. Despite these challenges, the quest for space-based computing is driven by the potential for groundbreaking scientific discoveries, new commercial opportunities, and the expansion of human presence in the solar system. As we venture further into the cosmos, our reliance on technology will only deepen. From life support systems to communication networks to scientific instruments, our ability to explore and understand the universe hinges on the reliable operation of our technological tools. Protecting these tools from the hostile environment of space is not just a technical challenge, it is an existential imperative. Investing in research and development of radiation-hardened electronics, advanced shielding techniques, and fault-tolerant systems is crucial for ensuring the longevity and reliability of space missions. Exploring new computing paradigms, such as neuromorphic computing and quantum computing, could lead to the development of inherently more resilient systems. International collaboration, data sharing, and the establishment of common standards will accelerate progress and foster a global community dedicated to overcoming the challenges of the hostile universe. The future of space exploration, and indeed the future of our technological civilization, depends on our ability to adapt and innovate. By protecting our technological assets, we safeguard our future among the stars.